So one of the root causes with fuel cells is water. This is total water flow. So you can all grab this paper. This was kind of published as one part of my dissertation. So in a sense is what goes on. These are all the these are all like the electro-osmotic drag models that exist for one of the modes of transporting water from the hydrogen to the air side. And there's several different models. They're all over the map. It's like asking three people what 2 plus 2 is and getting completely different answers on what 2 plus 2 is. So I had to find a way to decipher which one of these is actually correct. And then the back diffusion is the same way. There's so much inconsistencies with all these models. Which one is correct? I don't know. So, and part of the issue comes about when you measure the water flow across the membrane across the fuel cell. You're measuring it indirectly. So what happens when you're doing it to measure the water flow across the membrane, you have to measure mass flow in minus the mass flow out, which is equal to what we use as the total water transfer coefficient. So it's equal to the sum of both effects, sum of the effects that are present. So think of it this way, two numbers add up to three, but you have to tell me exactly what they are, and you can't guess at one of them. You have to determine one, then you can get the other. So you can't just say one's two, the other one's one. You have to mathematically determine it. So did a curve fit, realizing with the data, your total water flow across the membrane is non-linear, so it makes it more complex. So I had to work on the math to determine what these coefficients are. So I have data that's like this, that's nonlinear. I have data like this, which is nonlinear. And part of the reason that introduces this nonlinearity is the membrane properties are changing, like in a battery, and they're actually a function of the current density that the fuel cell is putting out. And also the phase of water is impacting what's going on. And your membrane thickness even plays a role in how the water flows going across the membrane. And I'll jump to the point. So like one of the experimenters said, hey, these are what the electroosmotic drag coefficients are. And they basically said, I don't have any, all the water flow is from one fluid driver, the electroosmotic drag. No back diffusion, none of that. So I went back and analyzed their data. And then keep in mind, so when I have water flow across the membrane, I can have temperature difference moving water, concentration, voltage, and pressure all contributing, not just two effects. So worked on a way to separate it out. So just with the math to solve for the coefficients, I replotted, here's a sample of how the phase of water affects how the water transport across the membrane. So here's the math and the details. I'll just get to the summary. So I replotted their data and found the data is not linear. And now, in fact, what I'm seeing is, hey, my electroosmotic drag changes with current density. People have not assumed that, hey, it's not changing with current density. This is pretty big. So depending on how you size the fuel cell and develop the fuel cell, this will also impact how much hydrogen ions I can move across the membrane. And these little red bars over here, they should be zero, but they're not. So they claim they've neglected the back diffusion, but it's actually present. So it's throwing off the model. So then people could be over predicting their water, under predicting the water, having to put a humidifier in the system, which could make the flooding even worse. And the best analogy I can explain with fuel cells is like the internal combustion engine when it first came out. It worked, we didn't understand it. The fuel cell was kind of like at that same way of of the internal combustion engine. I mean, the PEM fuel cell came out in 1969. We still don't fully understand exactly what's going on. And it works, but we don't understand why it works. And this stuff will kind of help make it work better.